So this is the third practice paper for synthesis and analytical techniques. So we start off with the multiple choice. We got propane reacting with chlorine as shown below. What type of mechanism is this? Okay, so first of all it's a substitution reaction because you can see you've substituted an H for a Cl here, and you'll know that that is going to be free radical substitution when it is a halogen adding to an alkane, because of course alkanes are non-polar, and therefore it is going to be radical substitution, which is C. Chemist reacts the following compound with hydrogen bromide. What is the name of the major product? Okay, so the major product, the hydrogen will add to the carbon which has already got the most hydrogens attached, which is that one there. So the bromine therefore adds to that one. And then when we are doing our name, our longest chain is like so. So that's going to be butane. And then coming off the second carbon, which is going to be here, you're going to have a bromo and a methyl group. So it's going to be 2 bromo, 2 methyl butane, which is B. So we're now going to react that compound with sodium bromide and H2SO4. This combination of course generates HBr in the mixture, and you replace the OH with a Br, so you get this product, and if you add all your relative atomic masses up you will get to A. What's the number of sigma bonds in a benzene molecule? So this may catch some of you out, but remember you have got a sigma bond 1, 2, 3, 4, 5, 6, and then the carbon hydrogens 1, 2, 3, 4, 5, 6, so 12 in total. Number of chiral centres, I've circled them. Remember, for a chiral centre you need 4 different groups coming from your carbon, and the answer is 6. Which compound cannot be hydrolyzed? Well, a compound that can't be hydrolyzed is of course a carboxylic acid. The others will be hydrolyzed to split up. For this one, the carbon-chlorine bond, this one, the carbon-nitrogen bond, and this one, the ester bond will be broken. So I want to make this compound from phenol. What do I need? First of all, I need to put a nitro group on here, and then you need to convert the nitro group to the NH2 group, and for the conditions for that you need C. Compound below reacts with hydrogen chloride gas at room temperature to form a saturated compound. What volume of hydrogen chloride reacts with 0.25 moles? For every double bond you need 1 hydrogen chloride. So you've got 2 double bonds, so you need 0.25 times 2 moles of HCl, which is 0.5. And then you times that by 24 because it's at room temperature and pressure. And as you know, 1 mole of any gas occupies 24 decimeters cubed, and therefore, because you need half a mole, you need 12 decimeters cubed. Systematic name of that compound, if you follow the red line along, you will see you've got 1, 2, 3, 4, 5, 6 carbons, so it's hex that we are looking at. This is coming off the second carbon then, so hexane 2-one, and this is coming off the 4th carbon, so 4-methyl hexane 2-one. The answer is D. So I've got this 2-step synthesis going on here. I've drawn this compound down there so you can see what it looks like. So you have converted the alcohol groups here into carboxylic acid groups here, but you've got rid of this double bond, and in the double bond place you now have this group here. So in order to get your carbonyl group, you could first of all add across your alkene. So you're thinking, how do I get from an alkene to a ketone? And the easiest step would be to add steam with a phosphoric acid catalyst. That would produce an OH group here, and then you would oxidize it, and when you oxidize it with potassium dichromate in acidic conditions and reflux, you would oxidize these 2 primary alcohols to carboxylic acids and your secondary alcohol to a ketone, and therefore the answer is C. Which reagent could be used to distinguish between ethanol and phenol? Use bromine water. because bromine water will not react with ethanol, but bromine water is of course a test for phenol, and when you react bromine water with phenol you would see a white precipitate and the bromine water would be decolorized. So how many peaks am I going to see in this NMR spectrum? So if we go through, we're going to see a peak for that one. Then these two are the same. So 1, 2. You're also going to see a different peak for these and a different one for that one as well. And then finally these two as well. So in total 1, 2, 3, 4, 5. The answer is C. Chloroethane reacts with an excess of ethanolic ammonia, which compound is the main organic product. You just replace the Cl with an NH2 group, so the answer is A. Which bond angles are present in this molecule? So I've drawn out here so you can see. So this bond angle is going to be 120 degrees. This one is 109.5 and that one is 104.5. So all of them, the answer is A. And finally then question 15, which terms best describe that molecule? Well, you've got a benzene ring there, so it's aromatic, and it's unsaturated, so 1 and 2. So moving on to section B now. Right, so define homologous series, same functional group with each subsequent member differing by a CH2 group. General form of the alcohols is shown there. Mass spectrum of A, alcohol A is shown below. So let's work this one out. It wants me to determine the structure of the alcohol A. So first of all, you look at your molecular ion peak, which comes in at 60. If you take 60 and minus 17, 17 is equal to an OH group, the mass of an OH group, you end up with 43, which is going to be C3H7. So you know you've got this C3H7OH. So you're either looking at it to be a straight chain, so propanol as I've drawn, or it could be propan 2ol like so. So we need to work out what it's going to be. And if you have a look at the X is 31 and X relates to C2OH. I should put a plus charge there. And so C2OH can only have come from propan 1ol. If you look at propan 2ol, which I will draw here, there is no way that you could have produced a CH2OH group from that. So mechanism for reaction of 1-bromobutane with sodium hydroxide. I've shown, don't forget your lone pair on your OH minus and your dipole on the carbon halogen bond, and that gives you your alcohol, which I have drawn there. I'm just going to change that to a better 7, like so. Okay, so what's the mechanism? It's nucleophilic substitution. And I can form this faster. What haloalkane would I use? I'd use 1-iodobutane because the Ci bond is weaker because it's much longer. Iodine is a much larger atom, and therefore the carbon iodine bond has got to be longer, and therefore it is weaker, and therefore more easily to break. So I've got to construct an equation for the formation of a chlorine radical from chlorotrifluoromethane. So quite straightforward, you're just going to break that carbon-chlorine bond and you're left with a CF3 radical. Then I've got to show how ozone is broken down. You would have done this in AS chemistry. So you start with an ozone, you react it with a chlorine free radical to give you oxygen and ClO dot. The ClO dot will then react with an oxygen atom to give you O2 and Cl. So I've regenerated my chlorine free radical, and this here is my overall equation. Okay. So, a research chemist found that 1 gram of chlorine radicals can break down 135 kilograms of ozone. Calculate the number of ozone molecules removed by 1. So first of all, you calculate your moles of chlorine. You then calculate your moles of ozone, which has been broken down. Don't forget to convert your kilograms to grams. So this is just mass over molar mass, and therefore you then do the moles of ozone divided by the moles of chlorine to give you the number of ozone molecules broken down by one chlorine radical is 9.98 times 10 to the 4. Don't forget they wanted 3 sig fig. So now I've got 5 compounds here, and I need to say which one is which. They've told me the structural formulae of the different ones I can choose from. So first of all, let's start with B. B has got to be molecule. Sorry. Okay. So let's start with compound B. B has the lowest boiling point. So you're looking at a molecule with only London forces, and one which is also branched as well. Because remember, a branched, if you've got the same number of atoms, same molecular formula, then if it's branched, it's going to have a lower boiling point. So your first one is going to be this one because it's branched and only has very weak London forces. This one is a straight chain, so has more points of contact, so it will be slightly higher in boiling point than B. So this one here is C. You're then looking at D. So D is going to be this one here because this molecule, 2-chloropropane, is of course going to have permanent dipole-dipole forces between the molecules, which are stronger than London forces. And then finally you've got to pick between these two. Both of them have hydrogen bonds between the molecules, but the hydrogen bonds between the alcohol molecules will be stronger than the hydrogen bonds between these molecules, these amine molecules here. So I put the order there, and in your explanation you just need to talk about the different types of forces between the molecules. So we're going to move on to alpha amino acids now. So what is meant by the term optical isomers is where you have two non-superimposable mirror images. And then they want us to draw it. So this is how I would start. I would start by drawing the carbon with the 4 bonds coming off, and then it really doesn't matter. So let's do, I've got an H coming off. I've also got an NH2 like so. I've got a CH2OH, and then finally I've got a COOH, and then just do the same for the other side, CH2OH, but just swap these two around like so. And then it makes it nice and easy for your examiner to see that you have got mirror images or non-superimposable images of each other. Right, so serine can react with the amino acid glycine to form 3 different products. What are those products? So I've drawn the different ways we do it. So first of all, here I have got glycine, and I've drawn serine next to it in a different colour. So the first thing it can do is it can form, of course, a dipeptide. And in order to do that, it's going to get rid of that, and then you will form a new bond like so, NH like so. And then you can do the same but in the opposite way. So I've just swapped these two molecules around, so I can just get rid of the OH and the NH2 like so. So there we go. That goes like so. There's my new bond, going to go in like so, and my NH like so. And then finally I can produce an ester. I've got an alcohol group on serine and a carboxylic acid group on glycine, so they form an ester like so. So I'm now looking at another alpha amino acid, aspartic acid, and I've got to draw the different products from this following reaction scheme. So I've drawn aspartic acid there, and notice it's got 2 carboxylic acid groups. So the first time I'm going to add, so for this first one I'm going to add some HCl. HCl will of course protonate the amine group as I've shown there. When I add excess methanol and sulfuric acid, that will produce, of course, an ester, but I will put an ester on both the carboxylic acids like so. So I've now got a unknown alpha amino acid which has got a branched R group. Okay, So it tells me that 0.03 moles of G has a mass of 3.51 grams. So because of that, I can find the molar mass of G, which is 117. I then take the 117 and I minus what I know all alpha amino acids have, which is this group here. So I do that and I'm left with 43. 43 would relate to this group, and I know it's in that configuration because it's told me that it is branched, like so. Okay, so it wants you to analyse this chromatogram and identify the amino acids. So you need to find the RF values of these two spots here. To do that, you measure the distance travelled by the spot divided by the distance travelled by the solvent front to find your two RF values, and you will find that they match these two here. Student runs a second chromatogram using a more polar solvent. What will be the effect of the R values on the amino acids? Well, your RF values are going to be larger because they're going to travel further on a larger distance on the chromatogram, and that's because the amino acid is going to be more soluble in polar solvents. So they're going to travel further with the solvent. So a student plans a two-stage synthesis of aniline from lactic acid, which they've shown there. I've got to get from here to here. So if you have a look at the groups, so your carboxylic acid group has not changed at all, so we're going to leave that. So all you're doing is you're changing an OH to an NH2 group. So if you look at your synthetic routes diagram, you're going from a secondary alcohol to a amine. And in order to do that, you first need to add HBr to put a bromine on it, and then you react it with excess NH3 and ethanol to convert the bromine into an NH2 group. Okay, so this probably isn't a mechanism that you've seen before, but you should be able to work it out. The key things to note is that you are looking at your final state of the CO2 group there. So the first thing that has to happen is, of course, the electrons have to come out of the benzene ring to attack the carbon, but carbon can't form any more than 4 bonds, and therefore one of the carbon-oxygen bonds must break, and it's going to be this one here, because you can see it's a CO minus group. Okay, so once you've done that, you then get to this intermediate here. You're going to lose the H plus to form your product. What type of reaction takes place in stage 1 and stage 2? Well, stage 1, they are both neutralizations. Neutralization in stage 1, the phenol is losing H+, and in stage 3, COO minus, your carboxylic acid group, gains H+. So I'm now doing a percentage yield calculation, or using percentage yield rather. So I'm going to prepare 4.83 grams of salicylic acid from phenol, and the percentage yield of that reaction is 45%, so I need to calculate the mass of phenol that we need to start with. So first of all, same old, you work out your moles of salicylic acid, which is mass over molar mass. Molar mass of salicylic acid is 138. So your moles of phenol that you need to use, you need to scale that up by 100 over 45 to give you 0.0778 moles. And then finally calculate your mass of phenol by times it by the molar mass of phenol, which is 94, to give you 7.31 grams. So I'm now going to react phenol with ethanoic anhydride. Remember, ethanoic anhydride is a very reactive, alcohol. So react with the phenol to produce an ester, like so. So you put C, double bond O, like so, and CH3. And what are you left over with? Well, you've used that part there. So you're left over with this with an H. So you're left over with ethanoic acid, like so. So those there are your two products. So what would happen if I reacted salicylic acid now with methanol? So if I did that, I would produce an ester, The carboxylic acid here would become an ester, as I've shown there, and I would need concentrated sulfuric acid to do that. How would I do that? How would I distill it? I put the setup there with the key thing, so it's not the best diagrams in the world, but it would do the job. Don't forget, water at the bottom, water at the top. So another reaction scheme here, again starting with benzene. First of all, I'm putting an acyl group on benzene. So in order to do that, I need an acyl chloride and an iron trichloride catalyst. I'm then reducing this carbonyl group down to an alcohol group, so that's sodium borohydride. To then remove that alcohol group to give me a alkene, I've got to dehydrate with phosphoric acid, or I could use sulfuric acid. And then finally, to do a polymer, it's going to be an addition polymer, so you draw it as the H shape. So let's do that, and I need to get rid of that double bond like so. Let's just get rid of it. Let's start it again. There, so going to be but then it's going to carry on like so, and that would be a repeat unit of the polymer. Remember, basically all you're doing is you're just getting rid of that double bond there and then just going like so. Okay, so polymer I cannot be disposed in landfill sites. It's not biodegradable. One way that we can process it, well, we can combust it for energy production. So a student's been given an aldehyde, a ketone, a carboxylic acid and 2 esters. I've got to identify the type of compound by carrying out some chemical tests. So first of all, how would I test for a carboxylic acid? Well, I've got to make sure that all the other ones will give a negative result. So I can use sodium carbonate for that, and I will see fizzing, and I put the reaction there below. Test for an aldehyde, of course, is Tollens reagent, and I will see a silver mirror. And again, you can use square bracket O for Tollens reagent, not worrying about the silver being reduced from silver plus to silver metal. And then finally, a chemical test for a ketone from the 2 esters. A 2,4-dinitrophenyl hydrazine would do the job, and I would see a orange precipitate. So the student wants to confirm that the other 2 compounds are esters. Unfortunately, there's no direct test, so those are my 2 esters. That's what they plan to do. So write an equation for the hydrolysis of one of the 2 esters. So I've put this one here. So when you hydrolyze, you obviously break that bond there. So you would make yourself the sodium salt of ethanoic acid, and you would also make your alcohol, which would be C, and then you're going to have 3 CH3 groups coming off like so. And you are going to also have your OH, like so. Suggest a chemical test on the hydrolysis product that will allow the 2 esters to be identified. Well, if you have a look, this one here that I've just drawn, this one is a tertiary alcohol, but if you hydrolyze this one, you would get methanol, which is of course a primary alcohol. And primary alcohols can be oxidized, tertiary alcohols cannot be oxidized. So you use potassium dichromate, acidified for that, and you would go orange to green with methanol, and there's the equation to give you, that would actually give you methanoic acid. So I'm going to change that along, so let's do that. As if by magic, there you go. We have now got methanoic acid, and we also make water as well. So could NMR spectroscopy be used to tell the difference between the 2 esters? Well, carbon-13 NMR could not, because carbon-13 would give you 4 peaks for both. You'd be a peak for 1, 2, 3, and then these 4. These would give you your 4 peak there. And the same, that would be 1 peak, that would be your next peak, that would be your next peak, and that would be that peak. So you see 4 peaks in similar sort of values. Could hydrogen NMR be? Yes, it could, because for this peak here, you would see a signal for these type of hydrogen there between 2 and 3 ppm, and that would be a singlet of intensity 3. However, for this one, you would see the signal of intensity 3, which would be a singlet between 3 to 4.2 ppm for that type of hydrogen. So hydrogen NMR could be used to tell the difference between the two esters. So I'm not keen on questions like this where it suggests all possible structures of the ketone and identify the aldehyde. It's nice to actually have one correct answer, isn't it? But never mind. So we do have a correct answer for the aldehyde, which I've shown here. So you've got to have all your hydrogens in the same environment apart from this hydrogen here. And the only way to do that is to have this aldehyde like so. For your ketone, you're just basically drawing the different isomers for the ketone, and I have drawn them below. So you've got 3 in total. Okay, so final question. Compound J. I have got a compound containing carbon, nitrogen and hydrogen. So first of all, we can do our elemental analysis, and if you do that, you will get C6H11N, which comes to, if you add all those atoms up, give the molar mass, you get 97. And if you have a look, that the molecular ion is 97, so that is a molecular formula. Now you have a look at the infrared spectrum, you will see a peak there for Cn, quite strongly there. So you know you've got a nitrile group in there. Okay, so we know we've got this group somewhere in the molecule. Then if we have a look at the NMR here, you have got a triplet and a quartet. So that is normally telling you you've got a CH2 group, CH3 group going on. You know, there's nothing special about them, is there? And then you've also got two, and then you've got a singlet there for your other hydrogens. So you've got 3 different types of hydrogen environments in your nitrile. You know you've got a CH3, CH2 group, and then so the other 6 hydrogens are in the same environment, so they're going to be 2 CH3 groups, and therefore that would be a structure which would work quite nicely. You've got your CH3, CH2 for your triplet quartet combination, your 2 CH3s in the same environment, and then you've got your nitrile group as well.